So welcome to lecture number 11 of our subject EC469 Opto-Electronic devices. So we are continuing with module number 2, laser. So in this lecture I am going to explain the line broadening of the laser and the different modes of the laser. So let's first look at the line broadening mechanism. As you know, the laser is formed by stimulated emission from high energy state to a low energy state when a photon is incident on the material. So it will give coherent light. So the energy of the emitted laser will be h into nu naught. So ideally speaking, if you plot the frequency versus intensity or the gain, then you should be getting only one line at nu naught, okay, because you are emitting only one frequency. So this is basically the case for one atom. Similarly, in the lattice there will be multiple atoms, but in the ideal situation all the atoms might be giving you only one frequency. But practically, when you plot frequency versus intensity, you will get a curve like this. Okay, and the middle frequency will be your nu naught. So this is the practical scenario. So you see that the line which was actually ideally the case where we should have a line, it has broadened to some length delta nu. So this broadening, let's say this is around delta nu, okay, and this is called as line broadening. Okay, so from an ideal case situation, practically you have broadened spectrum or you have broadened the frequency lines coming out of the laser. This is called as a line broadening. The main reason being, like, along with stimulated emission, there will be spontaneous emission also is possible in the atoms, which will give you frequencies apart from the stimulated frequency. So this frequency at nu naught, which has the maximum intensity, and this is due to the stimulated emission. Okay. So if you assume that the tail, both the tails, you can represent it by some nu naught minus d nu by 2, and this is nu naught plus d nu by 2 or delta nu by 2, where the total distance is now d nu. The spread, you can say, is basically delta nu. So delta nu is basically the line spread. Okay, so I could have written in terms of delta nu here. Okay, so delta nu is called as a line spread. Okay, and we also define something called as S of nu, which is called as line shape function. The line shape function tells us the shape of the curve that we are going to obtain. Okay, so this curve I can represent in terms of some kind of a function. That function is called as line shape function and represented as S of nu. And S of nu also gives the probability that the frequency of photon emitted or absorbed between nu plus delta nu by 2 and nu minus delta nu by 2. So S of nu is just like a probability function, where what's the probability that the photon that is emitted or absorbed lies between these two. So basically this is like a probability density function. So if I integrate from minus infinity to S infinity S nu of d nu, this is equal to 1. Since the frequencies are only along the positive axis, you have this is also equal to 0 to infinity S nu. Now, why this line broadening is happening? It is because of the different physical phenomena. Okay. Now, the broadening can be classified into two. First one is called as homogeneous broadening, and the second one is called as inhomogeneous broadening. So what do you mean by homogeneous broadening? So as we know that in any crystal or in any material you have multiple atoms, and there can be a stimulated emission from each and every atom. It might be possible that some of the atom might be giving you a different broadening spectrum. Okay, and it might be possible that all the atoms will be giving the same broadening spectrum. So I can define homogeneous broadening as the line broadening, let's say, as a response of each individual atom of the active medium, which is our gain medium, is same. Okay, so if you plot the broadening spectrum or line broadening spectrum of frequency versus intensity for each and every atom, you take first atom, you plot the spectrum, take second atom, you plot the spectrum, you can see that all of them will be same. Or in other words, every atom has the same central frequency. Okay. For example, let's take atom number 1. So it will have something like this with the central frequency u0. You take atom number 2, spectrum goes like this, again same u0. Atom number 3, you have the same spectrum, mu naught. Atom number 4, same spectrum, mu naught. So if you plot the line broadening or line spectrum of any atom in that lattice, you see that all of them will have the same broadening pattern. So in general, in the homogeneous broadening case, I can plot any spectrum as a single one, which has the central frequency nu naught, and all of them will have the same amount of intensity at the different values of nu. Okay, this is the homogeneous broadening. Now, what is causing this homogeneous broadening? Homogeneous broadening is caused by phonon interaction. So we have studied what a phonon is. A phonon is basically any kind of a lattice vibration will release or will theoretically give out a packet of energy called as a phonon, and phonon interactions will cause this broadening mechanism in the homogeneous broadening. So the phonon actually is divided into two. One is called as acoustic phonon, other is called as optical phonon. Okay. So to understand what acoustic and optical phonon is, let's consider a 1D lattice where you have atoms like this. Okay. Now these atoms are always in a constant state of vibration, and the vibration causes phonons. Now you can always mark vibration in terms of vector. Okay. So this can be, so the magnitude in vibrations are in this direction, and the magnitude is represented by the length of the vector. Next atom, it might be in the direction in this, next atom in this, next atom in this, and like this. Okay. But if you draw a line connecting all this, you see that it represents a wave. Okay. And this is called as a optical phonon. So in an optical phonon, adjacent atoms or adjacent atom displaces or vibrates in opposite direction. Okay. So if such kind of vibrations is there, basically you say that there is an optical phonon associated with this. In a similar manner, if you consider another lattice where you have 1D atoms, the adjacent atoms vibrates in the same direction. Or a group of atoms will vibrate in the same direction, the next group will vibrate in the opposite direction. So if you draw this, it will be something like this. Okay. And this is called as acoustic phonon. Okay. So it says group or groups of atom are displaced in opposite direction. Groups are displaced in opposite direction, and adjacent atoms are displaced in the same direction. If you consider a group, first group, second group, the first group will be displaced in one direction, the second group will be displaced in opposite direction. But if you consider only the adjacent atoms, apart from few, all the other atoms will displace in the same direction. And the homogeneous line width is given by A into T plus zeta optical phonon plus e raised to h bar omega LO by k T minus 1, where T is the acoustic phonon contribution, A is a proportionality constant, zeta OP is optical phonon broadening coefficient, h bar is equal to h by 2 pi, omega L0 is equal to optical phonon frequency. So you can represent the line width in terms of the contributions due to optical phonon and acoustic phonon, also in terms of the optical phonon frequency with the Planck's constants and Boltzmann constants and temperature. Okay. So like homogeneous broadening, we will also have inhomogeneous broadening. It means different atoms will exhibit different spectrum plot of frequency versus intensity. So there is a shift in center frequency of individual atoms. Okay, that means if I have the first atom, it will be like this, something around nu 0. Second atom, it will be like this, something around nu 1. Third atom, it will be like this, something nu 2. And fourth atom, it will be something like this, it will have nu 3. So if you plot the spectrum, or if you plot the frequency versus intensity, you see that it will be, so this is for nu 0, nu 1 and goes. So in general, the complete plot will be something like this. So this is called as an inhomogeneous broadening. This is mainly due to the imperfections or impurities in the atoms. Okay, you can say mainly due to impurities or different types of atoms. Okay, fine. For inhomogeneous broadening, the line shape function is given by or you approximate S of nu naught is approximately equal to nu naught by delta nu, where delta nu is the line width. Okay, so if you plot this, you can still have one center frequency somewhere, the one which having the maximum, that is your nu naught, and nu naught by delta nu will give you the line shape function. Now let's look at another most important property of laser, which is modes. Okay. So we have already seen that the laser will have mirror surface or reflecting surface. There will be some kind of a gain medium or an active medium, and there will be a pumping mechanism. So once the laser light is emitted, it will travel back and forth, traveling to the gain medium, and it will cause the laser emission. Now, although in this figure I have represented the light as a straight line, ideally it is an electromagnetic wave, which means there is a wave phenomena which is happening inside the laser cavity. So this whole thing is basically the laser cavity. There is an oscillation which is happening because the gain and loss of this whole cavity is equal at any point. Okay. So since there is a wave mechanism happening inside the laser, so there are multiple, or this wave mechanism should sustain oscillation. So a possibility is like there is a mirror, a wave might be starting from here and ending it here, and there will be a reflected wave which might start from here and end it here, or there can be another wave, only the half cycle is there, starting from here, ending here. Similarly, the reflected wave will be something like this. These are all possibilities of wave inside the laser. But if you look carefully, when I drew the waves, you see that at the mirror edge there is a node or a 0 point. Okay. So I can have another way. There is a mirror and my wave will be something like this. Okay. Is it possible? The answer is it is not possible in the laser cavity, because in this situation there is a constructive interference of the waves. The waves are getting added up. For having constructive interference, you need to have nodes at the mirror points. Nodes means 0 point. So there should be 0 crossing at the two mirrors. Then only there will be a constructive interference. If there is constructive interference, then only the wave can amplify and keep on oscillating. In this case, you actually have a destructive interference. Implies there is no oscillation. Oscillation means you have both gain and loss equal, because of which the wave produced will keep on going back and forth. Okay. So this scenario, if this scenario occurs, you cannot have a laser output. Only because of this scenario you will have a laser output. And if you look at the scenario again, you see that there is at least one half cycle of wave. At least one. Okay, because this is one half cycle, this is other half cycle. Similarly, in this wave, this is one half cycle and this is the next half cycle. For this wave, this is one half cycle, this is the next half cycle. And you will have a standing wave pattern due to constructive interference. Due to constructive interference, you will have a standing wave pattern. So how does a standing wave pattern looks like? So this is the mirrors. And you will have waves. Similarly, there is a wave from out. Okay. So it looks like a standing wave. It doesn't travel anywhere. So if there is a standing wave pattern inside your cavity, then the laser output is possible. So not all the waves are possible inside the cavity for laser action. It should obey some condition for the lasing action to take place. And what is that condition? The condition is or let's take a simple case where there is only one half cycle. So there is only one half cycle. So this comes here and this goes like this. So if the length is L, okay, so this first half cycle will have lambda by 2 length, okay, so this will have lambda by 2 and this will have the length lambda by 2, okay. So once it traverses a L plus L, which is 2L, the wave should have covered a distance of lambda. Next, let's take another situation where you have two half cycles, up and down. So if you look at this case, you see that there is lambda towards right and lambda towards left, okay. So you are traversing only 2L distance. This is L, this is plus L, this is 2L. So you will have 2L is equal to 2 lambda. Then another possibility is you can have 3 half cycles or 4 half cycles. So this is 1, my drawing is a bit bad. Okay, so here actually you have 1 lambda, 2 lambda, similarly in the backward also. Okay, so I can keep on writing this. 2L is equal to 3 lambda, 2L is equal to 4 lambda, and so on. So in general I can write the 2L should be a multiple of lambda, where m an integer multiple of lambda, where m can be 0, 1, 2 and goes. So this is the condition in which a standing wave will form inside the cavity and the lacing action will take place. Now here there is a special condition where we are assuming that there's a medium inside the cavity, and we are assuming that there's a refractive index for that medium. Let's say it is NR. Okay. So if there is an NR refractive index, I can modify this equation as 2L is equal to m lambda into NR. So this is the condition for having a mode, and this mode, where m is called as the mode. Of the wave. M lambda into NR, where m is called as the mode of the wave. And this type, where if this is the axis, the modes are along the axis. So this is called as a longitudinal mode or axial mode. Okay. This is called as a longitudinal mode or a axial mode. And it is happening because you will have a constructive interference during these modes. If there was a destructive interference, then this will not happen and you will not have a lacing action. So if I plot lambda, or we know that lambda is directly related to frequency. Okay. So basically I can write this as mc by nu into nr. Okay, whatever. So if I plot lambda versus intensity, you see that only for specific values of lambda you will get this. Okay, so this wavelength. So I'll have lambda 1, lambda 2, lambda 3, lambda 4. You will have the intensity. For it is not continuous. Only which satisfies this equation or this equation will be able to sustain the lacing action. All other modes, all other lacing actions will not be there. Okay. So, but we know that once after stimulated emission, you will have some kind of a line broadening mechanism inside that. Okay. But because of mirrors, the modes will occur only at specific frequencies or specific lambda. So because since you can directly relate lambda and frequency, I can say that for specific frequencies only you will have this light. So finally you will end up having something like this. Okay. So only for these values where the modes are allowed, you will finally having the lacing action. Okay. And there is a separation between the modes. So this is something called delta nu. Okay. So there is a separation between any adjacent modes, and you see our equation for nu is equal to C by lambda, where lambda is equal to, from this equation, 2L by m nr. So I can substitute this. This is C by 2L sorry, there is a mistake here. This is actually nr should come at the left hand side. nr 2L into m lambda. Okay. So here it will be 2L nr by m. So we will get C into m by 2L nr. Okay. For m equal to 1, nu is equal to C by 2L nr. For m equal to 2, nu, so this is nu 1, nu 2 is equal to 2C by 2L nr. So delta nu for any adjacent mode, you can say nu 2 minus nu 1, or that equal to any nu m plus 1 minus nu m is equal to, this is C by 2L nr. So the adjacent mode will have a frequency separation of C by 2L nr. So this is a very important equation which has been asked in many question papers, in many exams. So make sure you understand this concept. So any adjacent modes in the laser can be related with the length of the laser, the refractive index, and the velocity of the light. Okay. Similar to longitudinal modes, there is something called as a transverse mode. So what is transverse mode? Now, if I project the laser, so this is the mirror and there is a bumping mechanism, laser is coming here, incident back, goes forward, and some part of the laser will come out. Now if you have a photographic plate here, this is a, so photographic plate usually captures light. Then it will show as a dot whenever there is a lasing action. And you should understand that the full thing, the full cavity is not 2D but is 3D. Like you will have something like this. Okay. And this is complete mirrors. Okay. So there is an axis along the transverse field or perpendicular to the our normal axis. So in this photographic film, if you see the light, it will be something like this. If this is the film, then it can come like this, or if this is the film, the photographic plate, it can come like this, or again, if this is a photographic plate, it can come like this. Again, this is a photographic plate, it can come like this, and many such combinations are possible. Okay, so basically the wave that is giving out this kind of pattern or is basically a TEM wave, transverse electromagnetic wave, TEM PQ wave. Okay, where PQ, we'll see what this is. Okay, now if you consider this as P axis and this as Q axis, P represents and Q represents the number of nodes along P, which is P. Q means number of nodes along Q, where nodes is basically the 0 points. Okay, so in this case you see P equal to 1, Q equal to 1, because when you travel along P you cannot see any zeros. Similarly, when you travel along Q you cannot see any zeros. Okay, but if you look at this, this is P, let's say this is Q. When you travel along P, you see there is one node, there is a 0 point here. Okay, so this is P equal to 0, Q equal to 0. This is, so here the P value is 1, sorry, because there is one node, and the Q value is 0 because along Q there are no 0 points. You don't consider this along the middle where there is only 0 point. You consider it at least there should be some lacing activity. And if you look at the next one, so this is P, this is Q. So in this case the P value is 1, Q value is 1, because in both directions there are one node. So this is one node, this is another node for along P and Q. And if you look at this, this is Q, this is P. So here P is equal to 1, sorry, P is equal to 0, Q is equal to 1, because along the Q direction there is one node. So this is called as a transverse mode. But transverse mode in which you can see that you will have nodes when you travel along the different P and Q directions. Okay, so transverse modes are actually perpendicular to the longitudinal modes, and it can be shown in a photographic plate. Okay, fine. So I think we'll end the class here. So please have a look at or revise the lecture. Let me know if you have any questions. Thank you.